Hello and welcome. Today we'll demonstrate how to optimize costs in an engineering world using multidisciplinary optimization software. This is an approach to solve design problems by considering multiple factors or disciplines simultaneously before they're put into production. But cost optimization actually begins way before the factory floor and during the design phase. Of course, there's hundreds of parts potentially in any assembly and even assemblies of subsystems, making this kind of analysis seem extremely difficult. But fundamentally, the approach is the same, whether you're taking a look at the subsystem or the whole product itself. Whether you're making cars or consumer electronics and simple off-the-shelf items, the process is fundamentally the same. So let's get into it. In this video, we're not just doing cost reduction, we're doing cost optimization. Cost reduction means usually cutting wherever we can, which can easily hurt performance or reliability. Cost optimization is different. We use multidisciplinary optimization and find a smart trade-offs so we can invest where it actually adds value. All right, let's get started. We're working on a car suspension model. There are 4 key components that we can choose to tune: the wheel assembly, tires, and rims included, of course, the springs, and the dampers that together make the suspension model. A lot of data exists in simple tables, and here's ours. We have our 4 design variables that we solved for before in the previous video. That was the wheel mass, tire stiffness, spring stiffness, and damper coefficient. This column is what we optimized before. And what will make this multidisciplinary is now we're going to add in this cost panel. Our objectives are twofold. Firstly, we want to minimize the total cost of the selected parts and at the same time find the best suspension performance. The industrial AI process typically has 4 steps, but today we're going to jump directly into the results. When we look at the sensitivities, we see that what really moves cost overall is not the same thing that drives engineering values. This is the core challenge of optimizing 2 different disciplines. In the overall cost domain, we see that the damper suspension is the one driving the cost the most. While in the engineering domain, there are actually 3 parameters that the engineering department would care for tuning to make the best vehicle. This is actually quite common. The costs are driven by supply chains and all the intricacies of logistics. While the engineering domain is dominantly governed by the laws of physics. This explains why each of these analyses looks completely different. The underlying principles are different. So in this case, we'll do a neat trick to map 2 seemingly completely independent results against each other to find what we're looking for. This one scatter plot will show us the groupings of each of those discrete variables. On the y-axis, we can see the performance where lower is better as the travel of the tire. And on the bottom, we see the cost. So essentially the points of interest are the ones that have the lowest cost and the best performance. This local cluster of samples forms a stable optimum. This region represents the results of our optimization process. But that still doesn't answer our question, which inputs are the best? For that, let's turn finally to the parallel coordinates plot. This is a very, very neat diagram which compares our inputs to our outputs in one place. Let's get started with some interaction. As we mentioned, we wanted to minimize cost and minimize the travel distance the suspension travels. Here, we can actually interactively lower those parameters down and start to weed out the groups that are not interesting to us. And immediately we can see that only a couple of intersecting variables actually show us the inputs that produce the lowest costs and the best performance. And if we tighten our parameters even more, we can see the final candidates for our production line. This example is intentionally simple. The point isn't the exact parts, it's the process. Define your design space, let the optimizer explore it, then choose the trade-offs that fit your priorities. As long as you know what you want to deliver to your customers, we can help you optimize costs and performance. Cost optimization isn't a one-off project, it's a living process. Today, we looked at selecting parts with suppliers, but the same approach applies when you start swapping materials or even changing the manufacturing process. So as your designs, suppliers, constraints, and even your customers evolve, your optimization loop should evolve with them. We hope you've enjoyed this quick dive into the engineering world with us, and see you in the next video.